Wednesday, we're gonna keep talking about torque and different parts of the human body. So we're gonna try to do a couple more exercises, just so you guys get a little bit used to these kind of problems. We're gonna be using perpendicular forces in one problem, the same way that we did it on Friday, and then we're gonna be using we're going to be doing one when you need the moment of arm, and then you will see why you need the moment of arm. So hopefully we can do two, maybe set up three. And if there's any questions, if I'm going too fast or there's something that you need me to go and repeat, just let me know. We can do this over and over. This is one of the most relevant parts of the topic of the semester, especially if you are going for physical training or you're thinking about doing any kind of rehabilitation or anything. This is actually important. And if you're thinking about going to grad school, well, you will see this again. So I want to make sure that you guys get it. Anyway, so we're going to be doing this kind of problem. We're going to try to find what is the force on the bicep in order to keep an isometric position on this arm. And I'm going to assume that the arm is parallel to the ground. Okay. We have the following information. We know that the length of the arm is going to be 30 centimeters. The weight of the arm is going to be 3 kilograms. Sorry, the mass of the arm is going to be 3 kilograms. On one, at the edge of the arm, we have a barbell, and that has a weight of 5 kilograms. The bicep is inserted on the arm at a distance of 2.5 centimeters. Okay, and the angle between this perpendicular line to the arm and the muscle is 15 degrees. Okay, so again, we are trying to find the force of the muscle. We're going to try to find that force of the muscle. And we want an equilibrium conditions, under equilibrium conditions. Okay, and I know you know this already, but the equilibrium conditions are basically, we can write them as three equations. The sum of forces in x equals to 0, the sum of forces in y equals to 0, and the sum of the...
You didn't start screen sharing.
Oh, great. Thank you. Sorry about that, guys. Keep forgetting. Can you see it now, Trinity? Okay, so those are the three conditions. The sum of forces in x equals to 0, the sum of forces in y equals to 0, and the force of the torques has also to be equal to 0. So we're going to start with the force here of the muscle, and then what we're going to try to do is to find out a force here at the joint, what is called here joint reaction force. We're going to try to find that force later. Okay, let's start with the muscle. So, you want me to tell you, or you want to try on your own and see how far you go? Okay, give it a try. I'm not going to give you any more information. Let's see how you attack the problem. That will help a little thing for your exam. And And Trinity and Dylan, if you can do your work and then you show it to me on the screen, that way I can help you, or take a picture and put it on the chat.
So you're using two forces, right? You're using this force of the muscle. No, remember, this is your joint, then that force is going to be 2.5 centimeters in front. And it will be like 15 degrees from the equator.
Okay, so I think everybody has it, or have something very close to this. I'm gonna start with the free body diagram, and it's gonna be an extended free body diagram because I'm working with torques. I'm gonna put my origin at the joint. So I'm gonna have three forces, well, four forces. I'm gonna have the joint reaction force. I'm gonna put it like this. I have the arm weight, and I have the barbell weight. And this is going to be 15 centimeters, and this is going to be 30 centimeters. And then last, I have the force of the muscle. And this is going to be 15 degrees. So that's 15. This one is going to be 75. Okay. So your free body diagram should look something like that. Yes.
Where did the 15 come from?
The 15 degrees come here from the diagram, that this angle between the muscle and the vertical is supposed to be 15 degrees.
No, not that one. The 15 centimeters for the length.
Oh. So we're assuming that the center of mass of the arm is going to be in the middle. Yeah, it's going to be really good.
Okay.
So this one is not necessarily perpendicular, so you will need to find perpendicular. So your force is going to be high. Make sure that you change all your distances to meters. This is a very classic exam question, so.
Let's solve for the X and Y variables over the first and make a jumper.
For these two, you just have something like for this one, you want the perpendicular one. So it's not be,
Yeah, I don't think this is right.
yeah, this is going to be cosine, sine 75 or cosine 52.
Cosine.
Where you got the triangle?
Because you can't change this equation, so.
That would be these ones.
Now I understand.
Yeah.
Okay, so we're gonna do it really quick. So I'm gonna try to solve for this force M. And I'm gonna try to use this equation of the equilibrium of torques. So all the torques have to cancel each other. So I'm gonna have technically four torques. So I'm gonna have the torque of the joint, the torque of the muscle, the torque of the arm, and the torque of the barbell. And all of them has to be equal to 0. Because I'm placing my origin at the joint, this force, this torque is gonna go to 0. Doesn't mean that the force is 0, it just means that it cannot rotate the arm. And then I'm gonna end up with just these three terms. So the one that I think some of you are having trouble is to calculate the torque of the muscle. So to calculate the torque of the muscle, remember that I need the perpendicular component of that force perpendicular to the arm. So I need this component over here. I don't know what is the force, so that's going to be an unknown. And the distance that you're going to have between the joint and that force is going to be 2.5 centimeters. So that torque is going to be 0.025 meters. That's your inch of separation times the force, and then the perpendicular component of this guy. You can either do it cosine of 15 or sine of 75, either one. So I'm going to use sine of 75, and that one's going to be a positive torque. And the other two, the arm and the barbell, they're rotating the arm clockwise, so that's going to be a negative torque. So I'm going to have 0.15, and the force of the arm is going to be 3 times 9.8. The angle between this force and the arm is 90 degrees. So sine of 90 is going to be 1. So we don't do anything there. And then the last term is going to be 0.3 times 5 times 9.8. And that's going to be equal to 0. Okay, yes?
Oh, 3 just came from like the mass of the arm.
The 3 comes from the mass of the arm. Yeah. And from there, I can solve for the force. So I'm going to have okay. No, this number in the denominator is going to be very small. It's 0.025 times a number that's going to be less than 1. So this is going to be very small. So you're going to end up with a force that's going to be quite large. And Aubrey, what you got?
2953.
No, you got that?
No, I didn't, but I don't know.
Yeah, Jacob, you didn't get that? Anyone else got page?
Okay, so we just solved for the force of
The muscle, this force over here. So that's the force that the muscle is pulling up to keep that arm in that position. Not that I don't trust you, I just want to double check.
I mean, it's highly probable that I did mess it up. So
It seems that the range is correct. Oh. Yeah, me too. Yeah, I got the same. Yeah, that's what you got, Jacob. Okay, so still this force is significantly larger than the force of the weight of the arm and the weight of the dumbbell. Again, you have 8 kilograms, so that's going to be less than 80 newtons of weight. However, you have something that's almost 10 times larger to pull up. Okay, and again, the reason of that is that the insertion point is so small, it's so close to the joint that you need a much larger force uh, uh, to match the pull of gravity on the dumbbell. Okay, now, so now what we need to find out is what is the reaction force here at the joint. You can imagine that that joint is going to be also under stress. So even if that force doesn't cause torque, it helps on the equilibrium of the whole arm. Okay. So to calculate that, so to calculate the reaction force, or calculate force at the joint, we're going to be using the other two equations that we haven't used so far. So it's going to be the sum of forces in x equals to 0, and the sum of forces in y is going to be equal to 0. For this part, because we're not using torques, we can actually work with the AAA diagram, the one that we were working with the point model. So I can say, well, I'm going to have the force of the muscle here. I'm going to have the force of the joint. Again, I don't know which way it goes. I'm just going to make a guess, and I'm going to assume that's going to be in the first quadrant. And I'm going to have the weight of the arm and the dumbbell. Okay. So the sum of forces in X. In X, I'm only going to have two components. I'm going to have the X component of the muscle plus the X component of the joint, and that has to be equal to 0. The X component of the muscle is going to be negative 671.136 cosine of 75. And that's going to be equals to the X component of the joint. So I got 204.8 newtons. For the Y component, I'm going to do it over here. For the Y component, I'm going to have 4 components. So I have the Y component of the muscle plus the Y component of the joint plus the weight of the arm and the dumbbell, and all of these have to be equal to 0. Okay, so the muscle will be 791.36 sine of 75 positive. The joint, and then I'm going to subtract the weight of the arm and the weight of the muscle. The weight of the arm, the weight of the dumbbell. So this will be negative 3 times 9.8 minus negative 5 And that has to be equal to 0. And you can, so at the end, I end up with a y component of 686 newtons. Negative? Oh yeah, negative. Yeah. 685.9, something like that, negative. Okay, so so the force actually is going to be somewhere around here, and the angle, this angle is going to be 73 degrees. So almost opposing this force on the muscle. Yes.
Okay, I'm confused. Where did the 715.9?
This is the magnitude of the force. So I'm going to do it here. So it comes from just Pythagoras theorem. So this is the 204.8 square plus, what was it, 686 square.
Gotcha.
And the angle is the arctangent of the y component or the x component.
Thank you.
Yeah. Yeah, is it making sense? Okay. Now, there are other kind of problems. Like, for example, you try to, this is just the forces of an ankle. So you have someone that is just standing on tippy toes, and you are trying to find out again what are the forces at the joint. You're trying to find out what is the forces on the Achilles tendon. Okay. So here you have the Achilles tendon. Here you have the force of the joint, and you have the weight concentrated on the toes of the person. Okay. Now, in this case, if you look at the data or the information, we don't have any angles. Okay. So the question is, okay, so how do I gonna calculate these forces? So I'm gonna do the free body diagram. And instead of having my ankle, I'm just gonna represent the ankle as just as a bar. The pivot point is the ankle, so it's going to be somewhere around here. And I'm going to have the force of the Achilles tendon here. I'm going to have the normal force here. And I'm going to have the force here on the ankle. Or is it going to be here? I'm going to put it here. I just put it negative, but you can put it anywhere you want. Okay, now, usually we will need this angle over here. And then once you have that angle, then you can calculate what are the perpendicular components of each one of these forces. Okay, but in this case, we don't have that angle. And in real life, sometimes calculating that angle is not that easy. But what we have are these distances from where the force is to wherever the joint is located. So we know that between the toes and your ankle is 12 centimeters, and between your heel and your ankle is 4 centimeters. And this is something that you can actually measure in a patient. Just sitting down, you can measure these distances are not going to change. So if you have the ankle, you have your joint, and you have this distance over here. This distance, this 4 centimeters, this is going to be your moment of arm. So this distance over here this is also going to be the moment of arm. Okay, so the way you calculate the torque, if you want to calculate the torque of the Achilles tendon, is going to be whatever force you're going to have in the Achilles tendon that you want to find out, times 0.04 meters, and that's it. So remember, the torque will be the force times the moment of arm. Okay, so sometimes it's easier to measure this distance than actually measure the angles and to calculate the angles and look at the perpendicular forces. This is something that you can actually measure in a lab in real life. Okay, so we're gonna do this problem really quick. What I want to find out again is what is the force on the Achilles tendon, and I want to calculate what is the force on the joint. I'm going to assume that this person has a mass of 70 kilograms. That's like 150, 160 pounds. So, so again, what I'm going to do is, okay, I'm going to look at the forces. This force over here at the toes, that's going to be the normal force. So that's going to be equals to the weight, or the opposite of the weight is the force that's preventing me to go down into the ground. So this over here, this normal force is going to be basically the same as the weight of the person. So this is going to be 70 times 9.8. The joint in this case, the one that I'm going to pick, again, it is convenient if you pick the joint or that you put your frame of reference at a location of a force that you don't know. So you can technically put it at your ankle or you can put it at your heel. You can pick any frame of reference. You should not put it at the toes because the toes is actually one of the few pieces of information that you know. And as you put your frame of reference here, you're going to cancel that torque and it's not going to help you at all. So you need to put it somewhere either in the ankle or at the heel. So I'm going to put it at the ankle. And then here, I'm going to have two forces. This is going to be the force of the Achilles tendon. This is going to be the normal force. And it's not on scale. So this distance between the Achilles tendon and the joint, that's going to be 4 centimeters. And this one is going to be 12 centimeters. Now, when you look at some joints like the arm, the deltoid, uh, the knee, I think with the bicep is very obvious. Like the insertion point is usually of the bicep on your arm is around 2.5 centimeters, 3 centimeters. That's roughly more or less the insertion point. Your arm is 10 times larger than that, 30 centimeters, so more or less. So your muscle, your bicep, is going to try to do at least 10 times more force if you are holding something on your hand. Okay? It's just the ratio between the insertion point and the length of your arm. So 2 centimeters against 30 centimeters. It's around a factor of 10. So that means that your muscle is going to be doing around 10 times more force. In the case of the Achilles tendon and the normal force, the ratio is 3. So whatever force we have here, this force is going to be around 3 times. Not exactly, but around 3 times. Okay, just because the ratio and where the pivot point is. If you can imagine a seesaw with 2 kids, if you want these to be in balance, these two have to be the same weight. But if you have something like this, and this is 1 and this is 5, just in distance, then this little kid will have to be 5 times the weight of this guy to keep it in balance. So something like that happened also in this kind of joints, in this kind of levers. There's going to have to be a balance of the forces, there have to be a balance of the torque, and you can more or less estimate what is the ratio by looking at the distances of the arms. Okay? So we're just going to have to do the calculation and see whatever we expected, if this is really what happens on the equations. So again, I'm going to have the sum of torques going to be equals to 0. I'm going to have 2 torques. This torque is going to rotate counterclockwise, so this is going to be negative. Sorry, this is rotate clockwise, so this is negative. This one, the normal force, is rotating the foot counterclockwise, so this is going to be positive. So I'm going to have minus 0.04 times the force of the ankle plus 0.12, and the normal force is going to be 70 times 9.8, and that's going to be equals to 0. Okay, so solving for the force, I'm going to have 0.12 and 70 times 9.8 over 0.04. So you can see here, this is going to be 3 times 70 times 9.8. So it's 3 times the body weight on your Achilles tendon. So this is 2,058 newtons. Okay, so really quick, try to find out what is the force of the joint, this last force. What is the force that we have at the ankle? That will be your reaction force on that joint.
the reaction force, this third force. Then this one. Right, that one. Yeah, you only have one weight, that is the 70.
Oh, I did it wrong because I used that. I still had the same answer, so I was confused.
You can use any group.
Right, but this would have been 16 centimeters then.
Yeah.
So I messed it up, so I just
Okay.
changed it.
So, remember you have three equations. Some force x equals to 0, some force y equals to 0, and the torque equals to 0. So if you go with this one, so now you can use the other two. Now, these forces, because of the way they don't have x components. So the only one that you can use is that all the forces in y have to be equal to 0.
Leanne, you got? What you got? Okay, so again, we have three equations to solve these kind of problems. The sum of forces of torque have to be equal to 0, and then the other two is that the sum of forces in y and in x has to be equal to 0. Those are the only three equations that we have. Okay, these forces. These forces don't have any x component. Don't have any kind of x component. All of them are completely vertical. So we only going to have y component. So this equation, we're not going to use it. So we're going to have just the y component. Now, I don't know where is the direction on the ankle, that reaction force. So I'm going to assume that it's positive. Okay. Again, I have no idea. So the forcing sum is the sum of forces in y is going to be the force of the Achilles tendon plus the force of the joint that we want to find out plus the normal force, and that has to be equal to 0. Okay. Now the force of the Achilles tendon is the one that we just found, is the 2048. The force of the joint that I want to find out, and then the normal force, that's going to be 70 times 9.8, and that's going to, sorry?
686 for those.
Thank you. And that's going to be equal to 0. And solving for that force, I'm going to have 248 plus 686, or negative. So this will be negative 2,744 newtons. Yes.
It's 2058, not 48.
There you go. Yeah. Makes sense. We're gonna do another set of problems involving movement of arm Wednesday. In your homework, there are a couple. If you notice this homework, almost all problems are involving torques on parts of the human body. They're pretty straightforward, but hopefully that will help you kind of get used to the process of solving this kind of problem. Okay, questions? Okay. So we're just gonna do the first part. I don't know even you can see this. So we have the same problem that we start working at the beginning. A person with a dumbbell at the end of the arm, and we want to calculate what is the torque at the shoulder. There's a couple of information that we know. We know that the center of mass of the arm is going to be at 21 centimeters from the shoulder. The length of the arm is 56 centimeters. But in this case, the person is raising his shoulder or his arm 15 degrees above horizontal. Okay? The mass of the dumbbell is 6 kilograms. The mass of the arm is 4.2 kilograms. And the center of mass of the arm is 21 centimeters from the shoulder. Now, we don't have any information about the delta. We're just going to be part A right now. And the only thing that you want to know is what is the torque on the shoulder. We don't want to find out what is the force that requires to stabilize the arm or to hold it in position. The only thing we want to find out is what is the torque on the shoulder, okay? So I'll give you 5 minutes and then we'll do it at the end. Oh, yes. 15 degrees. So this is a much simpler problem. You don't looking at the forces that counterrace each other. You just want to know what is the torque caused by those two forces. No, the force is going to be tilted.
good. And then you can see this, this angle here. It's going to be 75. Yeah, yeah, that's. So you just want to find out what is the torque on the shoulder. Okay. Yeah, you want to count this torque on the shoulder. So it's not going to be zero.
Okay, so this problem is confusing because we usually look for conditions of equilibrium. And in this case, what I want is just the torque on the shoulder. What is a value of the torque? And what that basically means is that if you have your arm, you're going to have these two forces pulling down. And these two forces are going to create a torque here. Right now, we don't have the force on the deltoid to contrast these two forces and to make everything zero. We just have these two forces, and we want to know what is the torque here. So the distance here, we're going to have 21 centimeters. And the distance to the second force is going to be 56 centimeters. And this is going to be the force of the arm, and this is the force of the dumbbell. Okay. It's not that simple. Well, I guess I'm going to do it over here, just bigger. I'm just going to do the first force, the force of the arm. And this angle is 15 degrees. So again, the force that I care, the force that creates the torque, is the perpendicular force to the arm. So I need this force over here. Okay, if this angle is 15, this is going to be 90, and this over here is going to be 75. So 75 degrees is the angle between the force and the arm. So, and for the dumbbell, it's exactly the same, just the triangle is larger. So the torque of the arm is going to be, what is the arm? 4.2 kilograms times 9.8. Oh, sorry. 121 centimeters times 4.2 kilograms times 9.8 meters per second square. And then I'm going to use sine of 75. And that's going to be the torque. It's going to be negative. Okay. The torque of the shoulder or the dumbbell, sorry, is going to be very similar. So it's going to be minus 0.56 times 6 kilograms times 9.8 sine of 75, negative 2. And then I just add them together. And I get negative 40, 115 newtons meter. Okay, so if we didn't have that deltoid muscle, this will be the torque that they will be experiencing the shoulder. Wednesday, what we're gonna try to do is to add that deltoid muscle, trying to figure out what is the force on the deltoid. We're gonna do a couple of problems involving doing squats and different positions on the squats. And if you have any questions about your homework, bring it in and we can try to solve those problems too. That's it. Have a good day. See you guys on Wednesday. There's a survey on Canvas. Please don't forget to do that one.